Welcome. In this session, we'll take our simple line and point problem and we'll formulate it in a way that we'll refer to as a quadratic objective that has a linear constraint. Our problem was, so let's recall that the problem was we had a line that we could describe using a scalar argument, and we had a point W0. And what we wanted to do was find the parameter t, the argument t, that made L of t as close as possible to W0. Well, there's another way that we could do this, and we could turn this inside out. What we could do is say, well, what we want to do is minimize the distance, and then we have a linear constraint. So let's refer to this as a problem which has a squared length and a linear equality. And let's explore what we mean. Well, instead of parameterizing this with an argument, what we could do is say, well, suppose we take any vector in the vector space at all. Here it's a plane, and we take the difference between that and the given point. And now suppose that we take the squared norm of that. Well, what we would like to do is we would like to find an optimal point, which is the point of all vectors in the plane that makes this squared distance as small as possible. If we simply had this, the answer would be really straightforward, because we could observe that, well, when w equals w0, that this is the zero vector, no vector has a length smaller than the zero vector, so w star in an unconstrained optimization problem of this form is simply the point w0. Now, what we'll do is we'll add a constraint, and what we'll do is we'll say, let's represent that line as being this linear equation. So we had minus w1 plus w2 equals 4. Now we'll say it's this one form times w star minus 4 equals 0. And the reason for making it equal to 0 is that in optimization we often want this to be a general function, and it's easiest if we say it's equal to 0 rather than equal to some other value. So now what we've done is, so this is a constrained optimization. And let's be clear, this is the optimization and this is the constraint. So what we want to do is we want to find a W0 that is as small as possible and simultaneously satisfies this linear equation. In general, what we'll do is we'll write our linear constraints this way. So the way we'll have a convention, and this convention is not universal, but it will work for us. When we have equality, we'll write this as a matrix M times our optimal point equals a constraint vector C, and we'll usually rewrite that as M times the optimal point minus the C vector equals 0. And we're sort of used to this. What this means is that every entry of the, when we take M times W star minus C, that's a vector. And what we mean is that every entry of the left vector equals the corresponding entry of the right vector. So here, every entry of this left vector has to be equal to 0. And if we have an inequality that's a linear inequality, this would be a matrix A times our optimal vector, and we'll say that that has to be less than or equal to some B vector. And if if the user provides us with a greater than or equal, we'll just have to rewrite that so that it's always in this form. And in general, the way that we'll write that is A times the optimal vector minus B is less than or equal to the 0 vector. And here we're overloading the operator inequality. What we mean is that every entry of the left vector has is less than or equal to the corresponding entry of the right vector. So for this composite one, it will be less than or equal. Each entry is less than or equal to 0. Now, let's explore the geometry of this different way of posing the problem. What we can do is we can think of this squared distance as being a level of a quadratic form. And that the contours would be the points that satisfy the equation, which are the level curve at each level. So here what we've done is we've drawn the curve for level 1, the curve for level 2, for level 3, and for level 4. And we can see that there will be a level such that the points that are at that level, there is one point that also satisfies the linear equation. And so we could find that optimal level, and that would be a circle, which is a quadratic function, and a line, and then we could find the intersection, and that would be a different geometrical way of solving this problem. Now, let's take a look at a linear inequality. So here, the shaded region is the set of all points that satisfy a particular linear inequality. So what that means is that any point within that shaded region satisfies a less than or equal to 0 vector condition, and everything in this region does not. Now, if we take our contours, what we do is we can expand them again and again, and eventually we would find a point that just barely is within that feasible set. And so this is the geometrical interpretation that we'll have of equality. A linear equality is a level that satisfies a line, and then an inequality is a level that satisfies a half plane. In this case, it's a half plane, and in general, it's going to be a half hyperplane.